Welcome back, guys. In this lecture, we are going to discuss what is a test function and what are distributions and how can we make sense of distributional derivative. So there are like 2 to 3 things that we are going to discuss in this lecture. And this is lecture number 6. And down in the description, I will also add some homework problems, which if you solve and just tell me in the comment that you are done, then I can share my email or something related with you so that you can upload and you can share that with me so that I can check and tell you that okay, whether the solutions are okay or not. So let us start with the first definition. What do you mean by test function or space of test functions, which is denoted by d of some set omega. So omega is some set of bounded non-empty set in Rn. So in Rn, I'm going to take a set which is non-empty and bounded. So what is d of omega? D of omega is simply the functions which are C infinity with compact support in omega. So the functions which are smooth, continuously differentiable as many times as possible, and they have a compact support. It means on some compact set, they are non-zero, and beyond that set, the functions are zero. And we have discussed many examples. One thing else that I want to add is support of these functions is some set k, and this symbol is used for compact. So k is compactly contained in omega. So the support of each f should be some set k, and that k must be contained in omega and k must be compact. So whenever I write this thing, it means one thing is k is contained in omega, and second thing is k is compact. So this is how we define the space of test functions. And whenever we define a space, we also define some other notions on the space, like how do we define the convergence in these spaces and so on. So we say that, okay, a sequence phi n, which belongs to this d of omega, converges to, let's say, some phi, if what happens. So there are certain conditions that need to be satisfied for this convergence. One thing is that support of each phi n should be contained in k, and k is compactly contained in omega. It means support of each of these phi n should be contained in one compact set. Let's say that compact set is k for all n from the natural numbers. So this is first condition for convergence. And the second condition is phi n should converge to phi uniformly in omega. And third condition is all the derivatives of phi n. So these are all the alpha derivatives. So alpha is some sort of multi-index, you know very well. Should also converge to all the derivatives of phi uniformly in omega. So if these three conditions are satisfied, we say that, okay, this phi n converges to some phi in the space of test functions. So this is how we define a test function. So a test function is simply a C infinity function with compact support, and you define convergence in this way. Okay, so the next definition is the space of distribution. So these are not the probability distributions. Let me clarify this thing because there's a difference between these and those. So distributions, and this space is denoted by d prime of omega. So you might guess that this is some sort of dual space of d of omega because this involves functionals on that space. So what is d prime of omega? These are simply linear functionals on d of omega. It means some sort of functions which take some value from d of omega and give us output as a real number, and which is continuous in sense. So what is the sense of continuity? So this definition goes on for now, and I'm going to write if phi n converges to phi in d of omega. So if I have some test functions that they converge in d of omega, then if I take a distribution, let's say f, that I operate on phi n should also converge to f operated on phi for all f in d prime of omega. Since f is a linear functional, so I can say these things. This is how we define convergence in this space. So this space involves linear functionals on this. Hence, we call it d prime of omega, which is also called, let's say, dual space of d of omega. And I say that whenever phi n converges to phi in d of omega, then this action f acted on phi n should converge to f acted on phi for all phi in d prime of omega. This is how I define convergence in this space. And let me discuss a couple of examples. So we have already discussed this delta naught is not a function, as I told you. Delta naught is not from space L1. We discussed in the previous lecture, I think. So, but what is delta? So one thing is that delta naught is not in LP from, let's say, -1 to 1 for all P from 1 to infinity. So this does not belong to any LP. And we just proved this thing in our previous lecture. And what is delta naught? Because when you operate delta naught on 1, this gives you delta naught operated on 1 dx, and you know very well this will give me the result 1, but this is simply not equal to the L1 norm of delta naught. But like you can integrate delta naught, but in some sort of engineering sense, not in mathematics. Then you can say, okay, the L1 norm of delta naught is 1. But mathematically, we don't make any sense of integrating a Dirac delta function, which is delta naught. But we can only make sense of this thing in terms of action like this. From here up to here, we can make sense of this function in the sense of an action. So we can say that delta naught is a distribution, not a function. It's a distribution because we can operate that delta naught on some function which is C infinity. Okay. So what can we conclude? That this delta naught belongs to d prime of omega. So what are some of the properties of this function? You know very well, one thing is that, okay, if you have delta naught, you operate on some function phi of x. This will give you this function phi evaluated at 0. We discussed this thing in previous lecture. This is how you define that when delta naught is operated on a function, what is going to be the result for all phi from the space of test functions. And when I apply delta naught on, let's say, some C1, phi1 plus C2, phi2, I'm saying that, okay, is this linear? So the answer is yes, this is linear. This will give me C1, phi1 of 0 plus C2, phi2 of 0. So it is linear. And third thing is, so I'm going to check the properties, like what happens, can I check all the three properties? First thing is compact support. Second thing is, so this first thing tells me compact support because I'm going to operate this on some phi. I'm not going beyond that, so I'm good to go. It's linear, that I showed in the second. Now I'm going to prove convergence. So I'm saying that phi n converges to some phi n d of omega. Then what can I do? I operate delta naught on this phi n of x. This will give me this phi n evaluated at 0. Since phi n is a C infinity function, so this converges to phi evaluated at 0 because this is a smooth function. So phi n evaluated at 0 should converge to phi evaluated at 0. And this is simply delta naught operated on phi of x. So now I showed that, okay, this delta naught operated on phi n converges to delta naught operated on phi. This is how I define convergence in this space of distributions, you know very well, delta naught and phi n. This is called weak convergence. We have done these results in the very first and second lecture. The strong convergence, the weak convergence, and weak star convergence. Okay, so next example that I'm going to discuss is the sequence of mollifiers phi epsilon of x, which are from the space of test functions. You know very well, okay, these are C infinity functions with compact support. Then we say that, okay, these are some sort of functions from the test function space. Okay, we can prove one thing that might be part of your homework, that these phi epsilon should converge to delta naught of x. And now I have taken something from the space of distribution, space of test functions, you know very well, d of omega, but their limit does not belong to d of omega, but it belongs to d prime of omega. But delta naught belongs to d prime of omega. We know that thing. Okay, and why is that so? Why is that so? I can give you a little motivation that if I take phi epsilon to be some function, let's say, which is 1 and somewhere it is 0, I have to make it a smooth function. So I'm going to take whenever x belongs to some AB, where AB is contained in -1 to 1, and when x belongs to -1 to 1 complement, it means beyond that. This is a C infinity function, so I'm making it a C infinity function. How can I do that? I can do that in this way. So this is, let's say, -1, this is 1, this is A, and this is B, and this is somewhere here 0. But I'm not interested in 0. So from A to B, my function is 1. Wow. And from 1 beyond, and from -1 beyond, my function is 0. It's 0. And I'm going to make a smooth transition between these. I'm going to make a smooth transition between these functions. So it doesn't look smooth, but you can assume it's smooth. Okay, 0, 0, and this function is C infinity. You can see it has compact support from -1 to 1. It is C infinity with a compact support. So it's a function from this space d of omega. That's true, it's from d of omega. But what is the limit of this when epsilon goes to 0? So what happens when I take epsilon go to 0? Yeah, I think I missed one thing. This should be some b plus epsilon, and this should be some a minus epsilon, and this is non-zero up to here. This is non-zero up to here. Then as epsilon go to 0, this point a minus epsilon converges to A minus epsilon converges to A and B plus epsilon converges to B, and I'll get a function which has a singularity over here, exactly at B and exactly at A. So then I say that, okay, this phi epsilon does not converge to something in the space of test functions, but it converges to something in the space of distributions. So you should know that the space of test functions is a space with smooth functions, but when you have this function, when you take the limit, you get these vertical strips, and exactly at point A and B, your function is not differentiable. So you cannot make sense of this function at A and B in the sense of C infinity and in the sense of d of omega. Okay, so we have these couple of examples. Now we know what is a test function space of C infinity functions with compact support, and we know what is a convergence in those spaces. We know the space of distributions is a dual space on d of omega, and we call that distribution space is d prime of omega. And we did a couple of examples on that. I'm going to mention a lemma and maybe a couple of examples related to lemma. So lemma says, I'm taking f from d prime of omega. So it's an action. And for all k which are compactly contained in omega, there exists a constant ck, and n also depends on k, which is a natural number, such that whenever f is acted on phi, its absolute value is bounded by some constant ck times maximum of all the derivatives of phi, and x belongs to the compact set k, and the sum is over all alpha less than or equal to n of k. And we know very well phi is from the space of test functions, and support of phi is contained in k. So what can I say? If there exists an n from the set of natural numbers which is independent of k, so give me a number n which is over here n depends on k, but give me a number n that does not depend on compact sets. So whatever compact sets you have, you should get the same number n. And the smallest possible, so the smallest possible such n is called order of distribution. So such a smallest number n is called the order of distribution. Okay, so let us do a couple of examples related to this. So example is, I'm taking a function which is only continuous till omega bar. It means the closure of omega, which is from d prime of omega, since I can use this as an action, and my omega is bounded. So f acted on phi is f times phi dx. So you know very well that this integral is a real number. So I'm giving you an f. F is operated on some phi and it gives you a real number. Hence this f is called a functional, or the function from the space of distributions for all phi and d of omega. And you can simply check that all the integrals are linear functionals, and this is well defined. So this is linear and well defined. And how can I make sense of convergence? I can take a sequence that converges to phi in d of omega. Then how about f of phi n? It would be integral of f times phi n dx. And you can apply Lebesgue dominated convergence theorem to say that, okay, this converges to f into phi dx, which I can write as f acted on phi. So this f acted on phi n converges to f acted on phi. So this is how I can define the convergence or the weak convergence in this space. And how about the order of this distribution? I can simply check that, okay, f acted on phi, their absolute value is absolute value of integral f times phi dx, which is less than or equal to, what can I do? I can take the maximum value of f, maximum value of phi, and the measure of the integral. Since integral is on set omega, I can take omega, the measure of omega, maximum of f when x is from the closure of omega, and maximum of phi when x is from the closure of omega. So this is how I can define. And you know very well that, okay, maximum of phi, since phi is C infinity on some compact set, so maximum should be a fixed number, and I'm going to call that number a constant. And maximum of so I'm going to use maximum of f, not the maximum of phi, since f is continuous. So I can talk about this. So now I have maximum of, since this is phi, I can write this is zero derivative of phi when x belongs to some omega bar. And you know very well, okay, I can write phi as the zeroth derivative of phi. So I have the number here, the derivative order that I have is 0. So the order of this distribution is 0. So this is the order of this distribution. The second example that I have is f is a delta function, and you know very well this belongs to the space d prime of omega. And now what can I do? This delta naught operator, this is my function f operated on phi, is you know very well equal to phi of 0. And phi of 0 is less than or equal to maximum of 0th derivative of phi, where x is from some compact set. Again, you can also say that, okay, the order of this distribution is 0 because I have no derivative involved, so 0 derivative. The next example that I can give you is f from d prime of omega, and f operated on some phi is defined to be negative phi prime of 0. So this is how I define this distribution. And now let us find out what's the absolute value of this. You know very well it's going to be phi prime of 0, since I'm going to find out the absolute value on both sides, which is, you know very well, less than or equal to first derivative of phi, its maximum value, since it is one derivative. So you can simply say that, okay, the order of this distribution is 1. So the order of this distribution is 1. Okay, now the next thing is a definition that how can I make sense of convergence in d prime of omega. How can I make sense of convergence in d prime of omega? It means I take a sequence of functionals which belong to d prime of omega. We say this sequence converges to some function in this space of distributions and this belongs to a space of distributions. If whatever phi I take from the test functions, this phi n operated on phi should converge to f operated on phi, and this is named as weak star convergence. Since we are talking about the convergence of these functionals f, and we have already defined this when we are discussing, I think, our lecture on function analysis, we discussed what do we mean by strong convergence, and the convergence that we discussed before that in the terms of action is called weak convergence. And since this is convergence of functionals, we call it a weak star convergence. This will be really helpful when we are talking about different things. Okay, so the last idea that I'm going to discuss is called, so I'm going to use next page. What do I mean by distributional derivative? Distributional derivative. So I have f from d prime of omega. So f is a distribution. The question is, what is the derivative of f? So the answer to this is, can we differentiate? So first we have some very nice functions, we can differentiate them. Then we move towards the weak derivative. So the functions which are in LP or L1, we can weakly differentiate them. Now the functions which are not in L1, not in L2, not in LP, we have these distributions like functionals. Can we make sense of differentiation? The answer is yes. So the answer to this question is distributional derivative. So I'm taking omega from this Rn. So how can I say that, okay, there is some sort of derivative of f? So derivative of f with respect to some component xi operated on phi is same as negative of f and the derivative of phi with respect to ith component. And this is for all phi from the space of test functions. This is how I define the first order distributional derivative of f. So this is called first order distributional derivative of f, or the derivative of f in the sense of distribution. So I'm writing derivative of f in the sense of so this is the derivative of f in the sense of distribution. So if I have f, I multiply it with some first order derivative of a test function. You know very well test function is C infinity, so I can differentiate. If this is same as phi with an action from partial f by partial xi, then I call this function to be the distributional derivative of f, or the first order derivative of f in the sense of distribution. So let me put a remark that if f is from L1 and weak derivative, you know very well, if I take f from L1 space, then I can, it's not sure, but I can talk about the weak derivative of f. So if the weak derivative of f exists, it implies it's the derivative of f in the sense of distribution. It means the weak derivative, if it exists, implies the distributional derivative. So it's a simple thing. It's a simple thing. So let me tell you one thing, that if there is a bigger space, so this smaller space is the space of weak derivatives. It means if there is a weak derivative, it must be distributional derivative. But all the distributional derivatives are not weak derivatives. So these are distributional derivatives. Okay, if I want to define this thing in general, so I think this idea is clear that, okay, if there is a weak derivative, it is also a distributional derivative, but the other way around is not always true. So if there is a distributional derivative, it is not necessary that it's also weak derivative. So this is the space of distributional derivatives. It is not necessary that it is also a weak derivative. So in general, I can say that, okay, the derivative of alpha, derivative of f of order alpha is defined to be -1 to the some f operated on alpha derivatives of phi, and for all these phi from the space of test function, and this is called the alpha derivative of f, or the alpha order derivative of f in the sense of distribution. So this is alpha order derivative. And then I have maybe one remark or a lemma that says that, okay, let me put a remark. Fn belongs to the space of space of distributions such that Fn converges to f in d prime of omega, then d alpha of Fn exists. This is the first thing. And what happens now, I can also talk about convergence. And how can I talk about convergence? If I take any test function, then I take the derivatives of Fn and operate them on phi. Can I talk about convergence? This is my question. So the answer is yes. First thing is that I can take all the derivatives on phi, then like using integration by parts, you know this thing. -1 to the order of phi, Fn times alpha derivatives of phi. And you know very well, since phi is infinity, so I can differentiate it as many times as possible. And you know very well, Fn converges to some f in d prime. So I can say that this converges to f. So Fn converges to f in d prime of omega. I'm using this property here. Now I can just take the derivatives back, and I can remove this -1 to the alpha simply. You know very well, I'll be getting -1 to the alpha times -1 to the alpha derivatives of f operated on phi. And you know very well, -1 to the alpha, I'm writing here, plus alpha, this becomes -1 to the 2 alpha. And I can write -1 whole square whole to the alpha. This becomes 1 to the alpha, which is 1. So this is just basic thing. So this is d alpha of f. So what do I mean to say exactly? That all the derivatives of f, let me use another color, all the derivatives of f, n converges to the alpha derivatives of f. This is really a good thing. Okay, so here I discussed the how can I make sense of the derivatives of the distributions. So I talk about distributional derivative, and how can I make sense of convergence of these distributional derivatives as well? So these distributional derivatives converge. In Weak-Stock convergence, what do we say? Convergence in the space of distributions. So I have a conclusion, and the conclusion is okay. I don't know why problem. Okay, let me continue. So if Fn converges to some f in d prime of omega, it implies all the derivatives of Fn converge to all the derivatives of f in d prime of omega. Okay. Oh, I got it back. Sorry. So this is the remark that, okay, Fn converges to f in d prime of omega, then the derivatives of f n converge to the derivative of f in whatever the order of the derivative is. Let me quote final example, then maybe we are going to end it, and in the next lecture I'll be discussing Schwarz class and temporal distributions. So I'm taking Heaviside function, you know very well it's 1, sorry. So 1 when x is greater than or equal to 0, and 0 when x is less than 0. You know very well this does not belong to L1 over R, because when you integrate this on whole R, you get something which is not bounded, but this belongs to the space of distributions. So what can I say about the derivative of this Heaviside function? So how can I make sense of derivative? I will write h of x here, and I will write the derivative of phi with respect to x here, since it is only one component. Now let me check what this result gives me. So you know very well I can write this thing as simply Heaviside function integration from negative infinity to infinity and partial phi by partial x dx. And now you know very well this Heaviside function is only one when x is greater than or equal to 0. So I can write this thing as from 0 to infinity h of x is going to be 1, that I'm not going to write, partial phi by partial x dx, and I'm going to integrate this guy. The integral of the derivative of phi is phi of x, and I'm going to evaluate from 0 to infinity. So phi at infinity is 0 because it's a test function. Then I'll get 0 minus phi at 0. So phi at infinity is 0, and phi at 0 I'm going to write. You know very well I can write this thing as delta naught evaluated at phi of x. So Heaviside function is not an L1. This delta naught not an L1. So we cannot talk about their weak derivative. For weak derivatives, we at least should know that, okay, the function is in space L1. But we can talk about their distributional derivatives. So you have phi, the derivative of phi here. You have phi here. You have h here, and you have delta naught here. And there's a minus sign. So just comparing this with the exact formula that we discussed, we can say that, okay, the derivative of the Heaviside function is the Dirac delta function, which belongs to the space of distributions. So this is a main result that I just quoted now, and this result engineers use most of the times when they are talking about their results in physics and so on. This is really an important result for them, and at least for us as well, but not that much. Okay, so I will upload homework problems as well, and maybe in the next lecture, I'll also discuss the Shiva's class and temper distributions, and maybe after that we'll move towards Fourier transform. But before Fourier transform, we'll be discussing many more properties in these distributions and the properties of the Dirac delta function. So till then, goodbye, and see you soon.